So it's a pleasure to come here to the Bangalore International Center. Thank you for the invitation. I would like to tell you about one very exciting area of astronomy, which is the study of black holes. So I'm going to tell you about black holes in the universe. And to start with, let's just make sure we all understand what we mean by a black hole. So, very broad discussion. We know that gravity is an extremely powerful and all-pervasive force in nature. The whole universe is governed by gravity. Every mass pulls at every other mass, and there is a force pulling them together. And this force affects also individual objects. So like, for instance, there is this schematic diagram of a spherical ball of matter. This spherical ball has its own gravity, and it pulls on itself, like the Earth is pulling on itself, the Earth is pulling on us, and everything is trying to come down to the center. If there's nothing to resist, the whole of Earth will go down to the center and become a point. But of course, it doesn't happen because the material of the Earth resists, and the object reaches some kind of an equilibrium radius. All normal objects in the universe follow this principle. Gravity is trying to compress them down to nothing, but they have their own internal pressure which keeps them up. A black hole is something that violates this picture. That's shown here. A black hole is an object where this gravity which is pulling in is so strong that the object is unable. Physics says it cannot possibly resist in any way at all. It can try, but the gravity will always win, and the net result is all of the matter ends up in a point. Within classical physics, it's a geometrical point. Infinite density, zero radius, finite mass. That's what is called a singularity. So that is kind of at the core of a black hole. And so, there is no real surface. Instead, there is something called an event horizon, a pseudo-surface. And that's explained in the next slide. So this event horizon is kind of a surface that represents a kind of a one-way boundary. If you are out here, so this is my black hole, all the mass is here. This is my event horizon. If I'm out here, fine, life is fine. I can do what I want, I can go where I want, I can talk to anyone, send signals, etc. But if I cross this event horizon, then I'm gone. There is no way I can come back. There is no way I can send a signal back. Even if I shoot a ray of light, the light cannot escape, right? Of course, we all know this, but I just want to remind you that this is a very, very special kind of an object. In fact, I'll add one more sentence. Once I go in here, I cannot even say that I can live happily ever after inside. Even that is not allowed. Physics says once you've gone inside, you can only do one thing. You can go and die on the singularity in a very finite period of time. Okay, so this is what physics says. So the event horizon is a point of no return, not even light gets out. And of course, we can calculate what is the radius of the horizon. There's a little formula which comes from theory, which turns out to be around 3 kilometers if I had a black hole with a mass m equal to this symbol, solar mass, mass of the sun. So if I take the whole sun and made it into a black hole, it will have a radius of 3 kilometers. Okay, so this is our black hole. It looks like a crazy idea, but before I go into that, let's look at some numbers. So if I take the sun itself, right? It's got a mass of 1 solar mass. It has a radius of 700,000 kilometers. When the sun dies, it will become a so-called white dwarf. So, it's not dying anytime soon, nothing to worry about, but it will die ultimately, and it will form a white dwarf, 1 solar mass. That will be much more compact. It will be 5,000 kilometers, so, much more dense. The sun is only 1 gram per centimeter cube, just like, us or the Earth or water. But by the time you go to white dwarf, you're talking about much more dense material. If I had an object that became 1.4 solar masses roughly, it won't be a white dwarf, it will become a neutron star. that can be only 10 kilometers, very compact, but it'll still be a regular normal object. It'll have a surface, you can communicate, etc. And as I already mentioned, if I could say take that same solar mass, make it a black hole, which is allowed. We don't know of any such black holes in the universe, but it's allowed in principle. It would have a radius of 3 kilometers. So, we have normal objects which are not very different from black holes, but the black hole is very different because of this one-way street business. Now, we do have black holes of different masses in the universe. So I've given a couple of more examples. 10 times the mass of the sun, a very common, typical black hole. This kind of black hole will have a radius of 30 kilometers. Another common type of the order of 10 to the 8 solar masses, 3 times 10 to the 8 kilometers, just to give you an idea of the kind of objects we're talking about. Okay, so coming back to this crazy business, right? I mean, this is, as I said, I would be quite happy if I have the horizon and say, okay, once I go inside, I cannot communicate. Fine. Yeah, you go do what you want. But if that person is allowed to live a happy life in there, like a separate universe, that's much more reasonable. But physics says no. In fact, when I say physics, all the physics comes from Einstein's general theory of relativity. That's where the black hole solution itself arises, discovered very early on. And it says, beyond this horizon, all you can do is collapse to singularity. Looks crazy, looks weird. And in fact, Einstein himself, it came from his theory. There's nothing wrong with the solution. But he thought there must be more physics beyond his theory, which will somehow stop all this from happening. This black hole, he thought, was a nonsensical idea. Okay? What happened, and this didn't happen until Einstein died. Einstein died in the 50s. In the 1960s, suddenly astronomers came into the picture, and astronomers started finding black holes. Started as a trickle, hints that something funny is going on in the universe. These things I cannot understand by normal physics. It must be something strange. People started suggesting black holes, and everybody laughed because it's such a crazy idea. But it's caught on, and by now today, it's completely accepted. The universe has got black holes, not one or two, uncountable number of black holes in the universe. In fact, we know for certain that there are two kinds of black holes in the universe. There are so-called supermassive black holes with a range 10 to the 5 to 10 to the 10 solar masses. These are generally found in the very center of galaxies. Like our own galaxy, the Milky Way galaxy, right in the center, there's one supermassive black hole. I'll say more about that guy as I go along. Pretty much every galaxy seems to have that. And in fact, the first evidence for black holes came with the discovery of so-called quasars. This is what happened in the 1960s. Today we know, and even then people suspected, a quasar is a supermassive black hole. So that black hole is somewhere here. Okay, this is an artist's picture, which happens to be eating gas. So gas is flowing around, falling into the black hole, and it's becoming very bright and shining, and becomes an extraordinarily luminous and bright object. In fact, these guys are so bright, even though they may be pretty much at the other end of the universe, we can see them with our telescopes, and we study them. And that was a surprise already in 1962 when the first of these guys was identified. So bright, so far away, looks like a star, what's going on? So it was called a quasar. And so today we think quasars are these, we are absolutely confident that they are these supermassive black holes. Okay. Now in addition, a second population was discovered soon after. These are small guys, 5 to 100 solar masses. They are called stellar mass black holes. And there are many of these. So, there is one supermassive black hole in every galaxy, sitting right in the center, like the boss, it sits in the middle. And then there are all these others, about 10 to the 7 of them, maybe more, 10 to the 7. So 10 to the 7 of these smaller black holes floating around, but they are smaller in mass. People suspect that there may well be other populations of black holes. Maybe there are black holes in this gap. as a third population. We haven't found them yet. There may be black holes below 5. There may be black holes that are so-called mini black holes or, primordial black holes. People talk about all kinds. We don't have evidence of these yet. This is what we know for sure. Okay. Here is one more interesting fact. This is now physics, nothing to do with astronomy. Black hole, as I said, it's a solution that comes out of general relativity, but it's one of these absolutely pure solutions. You can make a black hole solution and you can't do anything to it. It's absolutely, completely defined analytically from the equations. And at the end of the day, you can describe your black hole with just a few numbers. So, black hole can have a mass, right? The mass, gravity, how much it pulls, that is described by mass. A black hole can have angular momentum, spinning. It'll be spinning. It has some angular momentum. You can associate a number with that. I'm going to call it J. A black hole can have electric charge. So you can give it a charge, Q, and in principle, you can have a black hole with electrical charge. But according to theory, that's it. You can't do anything more to a black hole and give it additional properties. There are only 3 properties that a black hole can have: mass, angular momentum, and charge. You can't put a little mountain on top of a black hole, for instance, to give a little extra detail. That's just not allowed. The black hole will be just a smooth object. And in fact, in astrophysics, we think electric charge will get neutralized in no time. It's irrelevant. So we only say there are 2 numbers, M and J. And there's a kind of a fanciful name given to this result. It's called the no-hair theorem. The black hole has no hair. So I'm going to explain, where this comes from. And I'm going to use Einstein's picture here. This is one of the famous pictures. Einstein, there are lots of funny pictures. This one, I don't know how he got this, but I think he went to a Van de Graaff generator or something, put his hand there, and his hair went out. So anyway, he's got a lot of hair, as you can see. It's all sticking out. So the exercise here is, how do we describe Einstein's head? Okay? And let's be physicists. Let's say we'll make life easy. We'll assume that it's just a sphere, right? His head is a sphere. And let's, I shouldn't say this, but let's assume he has no brains, okay? He has no brains, it's an empty head, okay? So I don't have to worry about what's inside the head, and I'll ignore his nose and mustache and ears and all that. So he just has a spherical head. And so, I can say, look, it's got so much radius, one number, so much mass, sure. Another number, and maybe I can say, look, that's all. I don't need any more information to describe Einstein's head. But he's got hair still, right? He's got all this hair, and think of it, I don't know how many hairs there are, but every hair is attached somewhere on the head, so I need to tell what are the coordinates where that hair is attached, and then I have to tell how long is that hair, what is its color, what is its thickness. So by the end of the day, if I want to catalog all the hair and just describe Einstein's head, not counting the brain, I'll still need a huge number of numbers. This is not the case with the black hole. You can say, okay, it's got 3 hairs. It's got 1 hair, which I can call with a number mass, angular momentum, and charge, but that's it. I can't put a zillion other hairs on top of this black hole, at least not within classical physics. So, people came up with this name, that the simplicity of black holes, instead of calling it the 3-hair theorem, they called it the no-hair theorem. And as I told you, in astrophysics, in fact, it's only 2 hairs, the 2-hair theorem. Okay, that's just a nice, interesting sidelight. But it does bring up the point that, when you find a black hole, you want to go measure its properties. The first thing you want to measure is its mass. Then you would like to measure its spin as well, and I won't have time to talk about that today. But today, let's start with the mass, because masses have been measured for a lot of black holes. I'm going to take one really striking example, which is the black hole in the center of our galaxy. It's an object called Sagittarius A star, a famous object, well known for many years. Initially, they didn't even know that it was a black hole. They had seen it in the sky. They didn't know what it was, but now we know that it is a black hole. It is sitting in the center of our galaxy, and now you can measure its mass. And this has been done in this incredibly beautiful series of experiments by 2 groups one from Germany, and one from the US. And I'm just showing a movie based on observations. The first announcement, the first incredible announcement in 2002 was based on what is shown in the screen. So I'll explain what's going on. So what we are doing here is we are pointing a telescope towards the center of the galaxy, taking a picture of the center of the galaxy and looking at the positions of all the stars. All these circles are stars. There are zillions of stars in the center of the galaxy. You just take a picture, where is it located? Then you come back after 2 months and take another picture. Then another 2 months, you take another picture. And then you make a movie. What are these stars doing as a function of time over a period of time? So you can see the time here. Starts in 1992, and it goes up to around 2002 when the first announcement was made. See? And what the stars are doing is they're moving around. Okay, that's not a surprise. The surprise is they are moving around, but not in straight lines, as if they are being pulled towards a central point. So take a look at this particular star. Okay, so it's moving like this in a curved path. It comes, zips around, and it's going back. Look at that. It's making some kind of an orbit, and clearly something is attracting it so that it goes around. Just like the Earth goes around the sun because of the sun's gravity. Here, it clearly indicates that there is some object here with some amount of mass which is causing this star to go around in an orbit. So once you recognize that, you can solve. And what they did was, they fitted Newton's gravity theory and got the mass of the black hole, etc. Remarkable paper. So these are the two groups. I will show another movie which is based on more modern data. So this will go up to closer to, I think, more recent, 2020 or whatever. So same story again. All of these dots are stars. This is the original star I was telling you about. By now, it has done almost 1.5 orbits or more. See, the thing now is going for 2012, 13, etc., etc. See, this guy is zipping around again. It's made a closest passage. Second time, it's going around. That's a lovely orbit around some object sitting here. And you can see all the other stars. So the beauty here is you can look at every single star individually, ask what is its orbit doing, and they're all orbiting around one point. And that point has a mass of 4 times 10 to the 6 solar masses. So that is the mass of our black hole. Sagittarius A star, this mysterious source, is sitting exactly there. So we know that it is a black hole, it is sitting where it is sitting, how much mass it's got, etc. I would call this the most famous black hole. Okay, so famous that it got a Nobel Prize. Not the black hole, the scientists, but I think the black hole deserves a part of the prize as well. So this prize, as you know, just a few years ago, 2020, was given jointly to Roger Penrose, who did very fundamental theory on gravity and black holes, and to the observational scientists, Genzel and Getz, who did those wonderful experiments with the orbits of stars. And this is the object, Sagittarius A star. Okay. So by the way, black holes is this enormous field, right? I'm just picking some topics here and there to talk about, and we can go into other things during the discussion. But one thing I'm completely dropping out of my talk is all the stellar mass black holes. I just decided I will go to the supermassive black holes, tell you a few things about them. But there is a huge story I could have told you about the stellar mass guys. Today we won't have time for that, okay? Sorry about that. Now, I've already said there are these supermassive black holes, not just in our galaxy, but everywhere. And here is the thing, this is actually now based on observations. You can look at the center of nearby galaxies. They all have something massive in the middle, and you can measure the masses. And there is somewhat indirect evidence that this is true even at large distances. So by now it's taken as a statement of fact. Every galaxy in the universe has a supermassive black hole in the center. And the range of masses we see is 10 to the 5 to 10 to the 10. Just 1 second, please. Okay. This was a surprise that turned up when these surveys were done. People went, they started finding black holes, they started measuring masses, and then they said, are these just random masses or is there any pattern to the masses? And they found a very surprising, or at least a pronounced pattern. And the pattern is shown, this is one of the versions of this pattern. Here what is shown is, in the vertical axis, the mass of the black hole. On the horizontal axis, some property of the galaxy. The black hole is sitting in a galaxy. And by the way, you all know what a galaxy is, right? Let me show you some pictures. Anyway, they're so beautiful. So here are all pictures of galaxies in the sky. Our own Milky Way galaxy, we can't take a picture because we are sitting inside it. But if we could, it probably would look, well, probably like this. Like one of these guys, okay? But it's an enormous object, 10 or tens of thousands of light years across, huge object with billions of stars rotating and doing all sorts of things. They can also come in other sizes, they can have just almost a spherical object. It's also a galaxy, it's just a huge number of stars. You can have something in between, this is what's called the Sombrero galaxy. Beautiful, they're all beautiful images, okay. So, there are all these galaxies. So you can look at properties of the galaxy. You can look at the mass, the luminosity, and in this case, it's something called velocity dispersion. But the point is, when you plot in a 2D diagram, black hole mass versus galaxy property, there is a correlation. When this galaxy property is large, the black hole mass is large. When the galaxy property is small, black hole mass is small. So, yeah, okay, that's interesting. They know about each other. The question is, how can it do this? It's a mystery because the galaxy, as I told you, is tens of thousands of light years across. We're talking about radii of black holes in maybe hundreds of thousands of kilometers, not light years, right? They are not at all in the same league. Black hole is tiny. Why should it care about the galaxy in which it lives? This has been it's now 20 years since this correlation was found, 22 years I think now. And people are still working to find out what is the reason for this. It's taken us a big clue on just overall structure formation in the galaxy. How does it work? So I'll just go through a few words, what might be happening. So the general scenario is, the universe forms initially very simple. It evolves, makes structure, stars, galaxies, black holes, etc., etc. These all form, grow, and in fact, they merge. Galaxies merge. They form as smaller objects, and then they merge over a period of time and become bigger and bigger galaxies. Our own galaxy would have gone through huge number of mergers in the past before it became what it is today. And if you imagine that each of these pieces had a little black hole sitting in the center, those would have merged, and they would have kept, accumulating and becoming bigger and bigger. And here is the story. The story is that when these guys merge and do things, they become very bright objects. This is the quasar. They churn up the gas, the black hole eats the gas. When the black hole eats the gas becomes very hot and it radiates, becomes very, very luminous, and it does other things. All that is energy. That energy can somehow go and modify the properties of the galaxy. This is still, I would say, a scenario. I don't think we have a complete detailed understanding, but it's a reasonable scenario that kind of works. And the idea is, end of the day, somehow, the black hole is able to modify the galaxy, and this is how they're talking to each other. Still, this business about the scale is a worry. The scale difference between the event horizon of a black hole and the characteristic radius of the galaxy, it's not a few hundred. It's 10 to the power of 8, okay? That's a large range of scales over which to communicate information and to influence each other. And I'll just leave you with an idea of what people think might be doing the thing. We think it is what are called jets. So here is the same artist's picture of what a quasar might be. Right? The black hole is here, a little dot. Gas is accreting. This is the guy that becomes bright. You see it with our optical telescopes. But these systems also can emit beams, so-called relativistic jets, which carry a huge amount of energy at nearly the speed of light. Okay, so this is something that has been known for a long time, in the sense we have seen pictures of these jets. So these are all radio astronomy images of a lot of famous systems. In each of these cases, so take this guy for instance. There is a supermassive black hole right here. There is some kind of a galaxy around it. But there is this beam coming out. There's actually a beam here as well. And all of this is emerging from the black hole as part of the accretion. Here is a nearby guy, M87, clear sign of a jet coming out, jets, so on. Many examples, and there are thousands of others we could add to this collection. So in any case, so this seems to be part and parcel of accretion, that there will be these jets. And the idea is that these jets are able to travel such large distances, you can see it in the sky, that even though the galaxy is huge, the jet is also huge, and it's carrying energy, and somehow that is able to churn the galaxy and then produce whatever modifications are needed, and thereby produce this particular correlation we talked about. Okay, so I would say, stay tuned. This is still work in progress. People are trying to understand, but this is state of the art right now. One other topic that people would generally be interested in is, where did these supermassive black holes come from? So I told you I won't talk about the stellar mass black holes, but that is a case where we do know where they come from. They come when stars die. When the sun dies, as I said, it will become a white dwarf because the sun is too small. But if I take a really big star, let us say 50 times the mass of the sun, when it dies, it will make a black hole. We can show this from models, and we see these black holes and the stellar mass black holes, the range of masses, etc. we see, kind of is reasonable. I think we have a good story for where the little guys come from. But where does this unique supermassive black hole in the center, where does it come from? Answer is, I don't think we know. We have ideas. When I say we, the community, okay? People come up with all sorts of ideas. There's no clear evidence one way or the other what's going on. It looks as if somehow, again, early in the universe when galaxies were forming, right? Part and parcel of that, something happens in the middle makes its own compact object, which becomes kind of a seed black hole, or I don't know what to call it, an intermediate mass black hole. People have names for it. Perhaps something like 10 to the 4 solar masses black hole gets formed spontaneously. I'll put that in quotes, we really don't know how, but I can say that. But once you make that, imagine that all these initial proto-galaxies each have their little 10 to the 4 solar mass core. Then through mergers, they will grow, they will eat gas and grow, and you can get up to 10 to the 10 solar mass black hole today. So, that may be where it ends up and what we are observing today, but exactly the origin is still pretty much an open question. It's one of the major questions for which people are building instruments that can look deeper and deeper into the past of the universe to see, if we can actually see these guys being born. That would be something. Okay, I'll leave that topic out. So I will now talk about Tarun mentioned the Event Horizon Telescope. It's another topic. Making a photograph of a black hole, right? So picture is worth 1,000 words. Some famous person said it. So in the case of black holes, I've said 1,000 words so far, I think, today. In my talk, maybe more. Let me, talk a little bit about making a picture. Accreting black hole, we already said. When I say accreting, gas flowing in, okay? gas flowing in to a black hole, and they all have gas flowing in, because there's gas everywhere in the universe. Some have a lot of gas, some have less gas, but they all have gas. They produce radiation because the gas gets hot. So if I got an object which is producing its own radiation and shining, I should be able to make a photograph or a picture of it. And before somebody is confused about, the black hole, nothing can escape. Once the gas falls through the horizon, then you don't see anything, right? That is gone. But in the process of falling in, whatever it radiates can reach us. That's what we hope to see, that we can see the radiation from the gas, and then it goes through the horizon and it goes dark because it's a point of no return, okay? So, can we make a photograph? What would it look like? And can you actually do it? Well, you know the answer to this. You know what it looks like if you remember at all. Tarun says every newspaper had the picture. I'll show the picture again, but yeah, that's the picture. And you know that it can be done because it was done. But let's talk a little bit about the physics. Why should it be in any way different from any other picture? So here, the key concept I want to mention is gravity can affect light rays. See, normally when I shine this laser pointer beam, it's just going in a straight line, right? Light travels in a straight line. Well, actually, no. Even this beam of light, because it's moving in the gravitational field of the Earth, is not going in a straight line. It's slightly bent, slightly curved. The Earth is pulling, and so the photons or whatever, the beam, is trying to bend towards the Earth. But it's such a tiny, tiny amount, we'll never measure it. So it's a straight line as far as practical purposes are concerned. But when you go close to a black hole, now we are talking about really seriously strong gravity. Then the bending of the beam of light becomes very pronounced. So in fact, if I go near a black hole, so this is the event horizon. So basically, if I went 1.5 times the radius of the event horizon, if I took a flashlight and shone it, let us say, tangentially, the bending will be so much that the light will go full orbit around and come back to where it started. I can form a circular orbit of this light beam just through the effect of gravity. So anything, radiation that forms and is emitted from this accretion gas near a black hole, that light won't reach us in a straight line. It'll kind of go off, get bent by gravity, and then it'll reach us. So that means the image is going to be distorted. It'll have its own peculiar, very unique properties. So here, for instance, this is a computer simulation. This is a simulation done by my student, Andrew Shale. And he said, M87, which is this big galaxy with a big black hole, what would it look like if we could make, actually a movie? Just look at it with very infinite angular resolution. What will the picture look like? So this is not practical, of course. Nobody has this kind of angular resolution, but you can do it on the computer. You can pretend. And the point here is, there is this gas. It is swirling around. There's all of this fluffy stuff that's going round and round. And then there is this pretty much fixed, permanent, circular ring. That ring is related to this orbit. So the existence of an orbit like this, a circular orbit around the black hole, is reflected in the image by a permanent circular feature, plus all this fuzzy stuff which is running around. And if I had more contrast, you could see it even further out. Notice that the center is black, dark. That's because nothing from the center directly reaches me. Radiation can go around the black hole and reach me, but it can't come through directly because there's the black hole there, it absorbs it. So there is this dark region in the middle called the shadow of the black hole. And that was kind of a really big prediction. It comes all the way back from Einstein's relativity. As an astronomical prediction, the prediction was made in 2000 that we should be able to do this. And the only question is, how do we actually resolve this exceedingly tiny object, which is very far away, with our telescopes? Seems like a crazy dream, but it turns out that you can do it for at least a couple of objects. One is this guy in the center of our galaxy, Sagittarius A star. The other is the black hole in the center of this M87 galaxy. Both cases, you can calculate what is the kind of size of this ring that you expect, which is extremely tiny. It may not be obvious to everyone in the audience, but that is a challengingly small angle to resolve with an astronomical telescope. But this is really what the Event Horizon Telescope, or EHT, set out to do. It's a very clever experiment. It is an experiment that, firstly, it starts with the requirement that we want to resolve such and such black hole. And you can calculate. So let us say you're going to do the experiment with radiation of wavelength 1.3 millimeters or 1 millimeter, okay? That's a good wavelength for various reasons. So you can calculate pen and pencil. If you want to use 1 millimeter wavelength radiation and make a picture of either M87 or Sagittarius A star, your telescope must be as big as the Earth, okay? Because there is a clear physics, wave optics relation between angular resolution that you can achieve and the size, aperture of your telescope. So it's an easy calculation. It has to be as big as the Earth. Now, a timid person would say, forget it. I don't have a telescope as big as the Earth. How can I possibly do this? But the radio astronomers who did this work, they are not timid. They said, what's the big deal? We have telescopes all over the Earth. There's even a telescope in the South Pole, which is doing fantastic work on lots of important problems. There are telescopes in Chile, in the USA, Arizona, Hawaii. There's one in Greenland, which our institute actually installed as part of this project, in Europe. So why not just combine all of these telescopes and call it a single telescope as big as the Earth? Well, this is a technique called interferometry, an old technique which has been developed. Until this project, it was not done on this scale over the whole Earth. But the idea existed. You have to be clever. You have to simultaneously observe with all of these telescopes the same object, carefully record the data, bring the data together and do huge amount of processing, analysis, image reconstruction, etc. Hard work, but doable, okay? So that's what this experiment attempted and succeeded in doing. It collected simultaneously data from multiple telescopes around the Earth at the same wavelength, around 1 millimeter, combined it, analyzed it, and produced results. This is the EHT. The first data were collected in 2017 on these two objects and some other objects as well. But this is the main story. The first results were published in 2009. It took 2 years. It took 2 years to really analyze and be sure that we had the right answer, okay? It's a very difficult experiment. And that is this famous image. Okay? That is this guy. This is the image of the black hole in M87. In fact, from this image, you can tell what is the mass of the black hole. 6 times 10 to the 9 solar mass. This is a real giant black hole. Just to recall, our galactic center, Milky Way black hole, Sagittarius A star, is 4 times 10 to the 6. Right? This is 1,500 times more massive than our black hole. It's in a neighboring galaxy. Okay? So this is this wonderful image. And the beauty here is you've got a ring-like feature. You've got a dark center, that is this famous shadow. And let me see if I can. what you should imagine is that that picture I showed you is really this guy, but blurred out. You're seeing a blurred picture because even with the size of the Earth, your angular resolution is not the infinite resolution that we are using here, where it is based on, on the computer you can do what you want, but there is a limit to what you can do with a real experiment. So imagine taking this and blurring it. What will the picture look like? Well, that was the picture that was produced, 2019. So this was a sensation, and this is the one for which the 2020 Breakthrough Prize in Fundamental Physics was awarded to Doleman and other members of the EHT. Okay, then it took a few more years before that same data, 2017 data, could be converted into an image of Sagittarius A star. So here now are the two champions. This is M87. This has got some more information now. There's polarization. I just won't go into that, okay? This is what the picture, photo of Sagittarius A star looks like. Same thing again, a ring. This is presumably the blurred out version of a real sharp ring there. We don't know, but that's what theory tells us. Definitely there's a dark center. The black hole is sitting there. Okay, and this has got a mass of 4 times 10 to the 6 solar masses. This is all still 2017 data, I guess, in this. Yeah, right. So there is data collected in 2018, 20 or 21, 23. And actually more telescopes are being added, so some of the later data are better quality. But this is such hard work. The public data or public results are still only based on the 2017 data. So this is where we are. So I asked, can we take a photo of a black hole? Yeah. We have two photos of two black holes. This is the first one, the champ, and this is our black hole in our own galaxy. So now you can ask, I better stop soon. Where do we go next? Well, one thing is obvious. We would like to do better, right? How would you do better? If you are restricted to the size of the Earth, then all you can do is you can make more telescopes, more stations to collect data, collect more data, more sensitive data, etc., etc. And this slide is all about that. I'll just mention in passing, there's another option which is also being explored, which is, why should we be limited by the size of the Earth? Why not send 1 or 2 telescopes up into space, right? Use a rocket, send it out. Maybe it can go out, into orbit around the Earth, not close to the Earth, but let's say far away, sufficiently far that it gives you an even bigger effective telescope. It's very, very challenging, okay, but it's easy to say it in words. But it's an idea that people are exploring. It's very expensive because sending anything into space is difficult, and making these kinds of experiments work in space hasn't been done before. So it will require a lot of experimentation. But that is a direction you can go to make sharper and sharper images. So you can reduce the blurring. You can start seeing the sharp ring by sending it to space. That's not what this slide is about. This slide says, okay, let's stick to the Earth, forget space. What can we do here? So what we can do is, instead of having just 8 telescopes, which is what I showed in the first EHT experiment, by today, EHT has got about 11 telescopes, added a few more. Let's go to something like 20 telescopes. Choose more locations. So, here it's a very busy plot. I borrowed it from someone. But this is the Earth. So, for instance, now there is a telescope in Korea. There's a new one in Europe. There are some additional ones in South America. There's one in Africa. And more in Mexico, USA, etc. There are good locations. Not good, but workable locations where we can put telescopes. So the plan is, why don't we try and use these sites, get additional telescopes. These will give you more information. and in addition, make the instruments more sensitive. This is really an electronics exercise. Just, you need to get more bandwidth, more sensitivity, reduce noise, all sorts of engineering issues. But all within the limits of what, technology can deliver. It takes dollars, money, rupees, yeah. But with, enough funds, this can be done. And this is a project that's got a name. It's called the Next Generation EHT, NG-EHT. And this is being heavily, pushed by the collaboration. Hopefully it will be funded and it will operate. I'll show you one slide what this might be capable of doing, okay? What can NG-EHT do? No, it hasn't been built, okay? So I can't show you real data, but this is simulated data. Again, Andrew Shale, my ex-student, he has created the simulations. So what's shown here is, take M87, that initial black hole. We know roughly what the accreting gas is doing. We can simulate it on the computer. In fact, Andrew did it for his PhD. And it's almost, I think it's the same simulation that's being processed here. So you can at least put all the physics you know and simulate the motion of the gas, simulate and sort of predict what kind of radiation might come out of it. And then what you do is, you say, look, here is my guess of what M87 might be doing as a function of time. Suppose I had NG-EHT and it observed this object. Let me pretend that I'm observing this object with the sensitivity limits and the arrays that I have. I'll take the data, treat it like real data, make pictures. What will I see? How well will I be able to do? What this shows is you will be able to do amazingly well. What's on the left is what his model predicts is the object. So this is supposed to be the truth. What's on the right is what NG-EHT would reconstruct. It would collect data from this guy, and then you'll go through all this process, correlating, reconstructing, and all that stuff. And you will get what's shown on the right. And you can, by eye, you can hardly see any difference. This is the little ring which we originally saw. What you see now is there's more dynamic range. You can see all this stuff outside. In fact, what's going on here is this is all the jet that's being ejected by M87. The black hole is sitting here. And watch all the details. They're all coming out beautifully in the reconstruction. So now the claim is, if NG-EHT is approved and operates, we will get actually black hole movies. We are done with photographing the black hole. That's easy, that's done. Okay, now we want to make movies of a black hole. But one thing I forgot to mention, watch the time thing here. Everything is very slow around M87. So the idea is you have to observe M87, every week or every couple of weeks for years. And then each time it will be slightly different. And then you can put it all together, make a movie. And something like this is what we expect to see. It won't be exactly this, because this was Andrew's best guess of what it might do. The real thing will do whatever it wants. But the point is, with an instrument, you can observe it, get the whole movie, and then try and understand what is the physics behind all of this. So we think this is the next frontier here. Time to move on from still photos to movies. So I will stop at this point. I think that's quite enough for this talk, because I'm sure you all have questions. We should have time for discussion. But here is a brief summary. Black holes are mysterious. I say maybe mysterious. Look, they are mysterious. Even the deepest physicists, in fact, the deepest physicists are the ones who think they are most mysterious, because there are so many puzzles. So they are mysterious. But the surprise, and I wish Einstein had been alive to realize this, they are real. We actually have found black holes. They are there in the universe. We have to deal with them, okay? So in astrophysics, we have these two classes I mentioned, of which I focused on this guy, this category. the supermassive black holes, there is this most interesting connection between the tiny black hole in the middle of a galaxy and the whole galaxy, which I think has got lots of interesting implications for how the universe itself evolves and the role of jets. And then we are now making pictures. Hopefully we will make movies in the future of black holes. So the future, I think, at least one of the directions for the future is the era of black hole movies. So I'll stop there. Thank you.
May I request anyone who has a question to just raise their hand? I'll bring the mic around. Professor Narayan, maybe you can just pick and I'll...
No. I'll leave it to somebody else to do the picking.
Hi, Professor. Thank you so much. That was an amazing talk. You talked about quasars as being able to generate like a lot of light, which we are able to observe. How are they able to generate light, and what makes a quasar able to generate light and not like a supermassive black hole that's at the center of our galaxy? So yeah, just...
Yes, so let's go back to this picture. Okay. So the process itself is basically this gas gets trapped by the gravity of the black hole. It goes into orbit. And then it, through kind of frictional forces, it kind of slowly spirals in and comes in, and falls into the black hole. Now, in the process, as it falls in, it becomes very hot. And you can calculate how hot, how much energy will be released just through this inspiring process. So when it gets hot, it will radiate, okay? And in a system like this, which is a classic standard model for these systems, basically something like 10% of the so-called rest mass energy of the gas will come out as radiation. So as a result of that statement, how bright it gets depends on how much gas falls in. For a supermassive black hole, if I send in 1 solar mass of gas every year, it'll produce, 10 to the 45, 46 ergs per second, which is an extremely luminous quasar. So the bright quasars, which were initially discovered, these happen to be supermassive black holes relatively far from us that were eating gas at a very high rate. So when they eat at a high rate, they radiate at a high rate, and they become extraordinarily luminous. Our galactic center is also eating gas. In fact, you need that gas to even make the picture, right? But for various reasons, it is not eating at the same rate as these guys. So our galactic center, I think, is right now eating, I want to say 10 to the minus 9 solar masses a year, something like that, okay? 10 to the minus 8 to 10 to the minus 9, many orders of magnitude less than the classic quasar. So it's the same, you can have a big black hole. I can make it very bright by giving it a lot of gas. It'll be dim without a lot of gas. And that's the main distinction. There's lots more details, okay? That's for the specialists. But this is the broad answer.
Hi. Is it on? Okay. Yeah, really enjoyed your lecture, and thank you. My question is, studying black holes have added to the theoretical understanding of physics, but are there any practical applications for studying black holes, for space travel or any other future endeavors? So is it just theoretical?
I would say at the moment, it is a pure intellectual, theoretical enterprise. All of physics really is that. But as you also know, physics has repeatedly turned up totally unexpected things, which then became of great practical importance. Starting with electricity and magnetism, right? Where would we be without electricity today? But it was just a field trying to understand some phenomena, and quantum mechanics and everything we do in our lives today is based ultimately on fundamental physics discoveries. In the case of something like black holes, the applications are not at all obvious at this point because their scale is different. They are based on gravity, and we are on too small a scale to really tap into gravity as a source of anything useful. On the other hand, they lead to enormous understanding of physics, and there was certain to be a spin-off somewhere which would be practically useful. But I'm not going to tell you that you should be interested in this because it's got great practical importance. No. I'm asking you as a human being to say, look, I'm a curious human. I want to understand how the universe works. What makes everything tick? Here is an interesting problem. What makes this tick? I'm giving you some of the interesting ideas there. So for me, it's just the curiosity and the amazement and just the intellectual wonder. Yeah. There could be applications, not anytime soon.
Thank you very much. It was an extremely interesting talk and throws up too many questions, so I can't ask so many. So maybe of all, I'll ask one. You showed the stars going around the supermassive black hole. Now that means in the galaxy, all the stars are going around that. In every galaxy, all the stars are going around the supermassive black hole, including our galaxy, the Milky Way, is going around the supermassive black hole. That means all the stars in the supermassive black hole are going, including the sun. And the Earth is not only rotating around the sun, it is rotating around the supermassive black hole. How long will it take to go around the supermassive black hole?
Yes, nice question. Okay, so I told you that the black hole is really a tiny little fellow in the middle of the galaxy, right? So a star which is near that black hole feels primarily the gravity of the black hole, and it goes around the black hole. The sun is not near the center of the galaxy. Sun is out here, 25,000 light years away, okay? So of course, the sun will feel gravity from the supermassive black hole, but it's a small amount. The sun feels primarily the gravity from the whole galaxy. See, the galaxy itself, you should think of as an object which is held together by gravity. All the stars in the galaxy and the gas and everything else, the dark matter, they are all gravitating, and they all collectively make a gravitational field under which they are moving. So the sun moves under the combined gravity of everything in our galaxy, including the supermassive black hole. And yes, the sun does go around the galaxy. We know it, we have measured it. We are going around. And in fact, I think it's about 200 million years to make one orbit around our galaxy. And the sun has been doing many such orbits over the age of the galaxy. Yes, so the statement you made is correct. Not just our sun, every star in the galaxy is orbiting the center in some fashion or the other. But you shouldn't think of them as all just orbiting the supermassive black hole, because by the time you come to these distances, the mass is no longer dominated by the black hole, but by the entire galaxy.
Hello, sorry. I just wanted to know your thoughts on the recent controversial paper that came out, Do Black Holes Have Singularities? Where he claims that there are counterexamples to singularities, and there is at least one event horizon that does not end in singularity.
That is it's a big theoretical question that's been around for many years. The Nobel Prize was given to Roger Penrose for his so-called singularity theorem. So just to go back, I said Einstein was very unhappy with black holes. He had many reasons, but one of the things was, even though people showed that if you take a spherical object and let it collapse, it will become a black hole, a so-called Schwarzschild black hole. And that's the kind of black hole I showed a picture of. All the mass goes into a point. He and many others wondered, what if it was not so perfectly spherical? If it is slightly distorted, maybe it will miss the center. Maybe it won't make a singularity. What will it do, right? So can I avoid a black hole or avoid, everything, horizon itself by just changing the initial conditions, making it more realistic? So what Penrose showed in his famous theorem is that if you have a so-called trapping surface or trapped surface, then you will form, I'll call it singularity. He called it really geodesic incompleteness. This is all technical stuff. You don't want to know these details, okay? But it's an absolute theorem subject to certain conditions. And that is the Penrose theorem. And I think if you accept his conditions, you can't avoid the singularity. But people also recognized that if you violate some conditions, make negative energy or negative pressure, make weird assumptions about the properties of matter, then you can avoid black holes, you can avoid singularities. This has been known, and there are some old solutions, already I think 1970 or 75, where you can have a horizon but no singularity. Okay? And then there are people who have been talking about you can have a singularity but no horizon. Okay? So there are all these discussions, and this latest controversy, I haven't followed it in detail. My guess is it's partly in the spirit of these other counter models where you invoke weird matter. So, for instance, I said a black hole has this property that once you cross the horizon, you can no longer have a stable object. It has to go and fall into the singularity. Now that has to statement is based on the assumption that the object is made of regular matter, normal matter, stuff with positive pressure, and positive density. If I throw away those rules and I say, look, I can have negative mass, or I can have negative pressure, or some crazy properties, then I can probably allow these stable solutions, but then you're really pushing your theory too far. So I won't say I know what the latest, I've heard about it. I haven't had time to study it, but my guess is it's in that spirit, that you can, of course, change the conditions or assumptions, maybe get over it, but from the practical man's point of view, the singularity is something we cannot study because it's behind the horizon. So we can only ask whether there is a horizon. If there's a horizon, it's a black hole.
Yeah, can you hear me now? Yeah. So, sir, my question is about the sound. NASA released the sound of black holes as well, I think a few years back. So, from where it is coming from?
These are probably gravitational waves. I'm not, again, sure what you're talking about. I've been traveling. You say it came out a few days ago? I didn't. Few years ago. Okay. So, this is a whole topic in itself, and maybe somebody has given a talk on this at some point. This is another Nobel Prize, right? So this is the Nobel Prize for gravitational waves, which was given in 2017 for this amazing discovery by LIGO, a laser interferometer experiment, which discovered gravitational waves. So the particular event that they discovered was two black holes, each about 30 solar masses. They are going around each other. Actually, they are spiraling in towards each other and merging. And while they are doing that, they are emitting gravitational waves. Okay? So that's what this picture is. This is a computer simulation of what happened which produced these particular famous signals. Now, you can easily convert, these are gravitational waves. So they are not electromagnetic waves, and I don't think they are acoustic waves either. They are gravitational waves, but you could convert it into an acoustic signal. Yeah, okay, here it is. This is the frequency of the signal versus time. So over a period of a fraction of a second, it produced a signal that started at low frequencies. This is kind of near the limit of what we can hear with our ears, and went up to 500 hertz, which is kind of beautifully in the middle of what our ear likes to hear. So I'm sure people have converted this signal into an audio signal. This could be, I don't want, NASA might have had something else in mind, but if I had to make the sound of a black hole, this is what I would use. I would take this signal, convert it into an audio signal, and get what is called a chirp. Zoop. It'll start low and then go up into high frequencies. So that is this thing, chirp. Okay, so that is one way in which you could visualize, but it's a visualization aid. It's not really a sound wave, okay? It's a gravitational wave. It's a wave in the fabric of space-time. Convert it into either light to help visualize or sound to help visualize, you can do it. Don't know whether that helps. If somebody knows more about this, I would be happy to be educated, but here is my best guess.
Professor, back here. Hi.
Hi, my name is Lucas. I have a question. What happens when a black hole sucks something?
That's a great question. What happens when a black hole sucks in something? Yeah. So, let's say I have a ball and it's falling into the black hole, right? So the ball is out here. It looks like a ball and you can see it. Great. As it falls in towards the black hole, what happens is the part of the ball that's closer to the black hole gets pulled more because gravity is very strong closer to the black hole. So the ball becomes stretched out. So it becomes kind of more like a cylinder. So it starts like a ball, it becomes longer and longer, elongated, and then becomes really stretched out, falls through the horizon, and disappears. So when you look at this ball, it just appears to get stretched out like a spaghetti, is what people like to say, and then it falls in, and then you don't see anything because after that, once it's gone very near the horizon or through the horizon, you don't see anything at all. So what you see is a big stretching and then silence. So Lucas, that's really what I would expect. You're welcome. Here.
Hello, sir. I just want an information. Is Andromeda Galaxy the nearest galaxy to the Milky Way galaxy? And what is the supermassive black hole of Andromeda Galaxy called as?
Great. Okay. Andromeda is the nearest big galaxy to Milky Way. It is slightly larger than the Milky Way galaxy. And in fact, let me just 1 second. This is a picture of Andromeda Galaxy. So this is our neighboring galaxy. It is roughly like our galaxy, but a little bit bigger. And so it's the nearest big galaxy. But there are a whole lot of smaller galaxies, so-called dwarf galaxies, which are around our Milky Way galaxy and also around, in fact, Andromeda itself. If I remember right, this is a dwarf galaxy which is in orbit around Andromeda. Right? So Andromeda has its own collection of smaller galaxies which are orbiting around. We have our own collection of smaller galaxies. And in fact, we and Andromeda form a so-called group, a single entity together. And so there are smaller entities inside that, dwarf galaxies. So galaxies come in all range of sizes. But if you say Milky Way-like, yes, this is the nearest galaxy. In the center of, this guy is called M31, okay? So in the center of Andromeda galaxy, there is a supermassive black hole. The latest I have seen, best guess mass for that black hole is about 10 to the 8 solar masses, okay? So does it have a name? I think in analogy with these other guys, it's called M31 star. So M31 is the galaxy, and M31 star we tend to use for the black hole in the center. Now our guy is special. Sagittarius A star is special because it was discovered even before we knew it was a black hole. It was discovered as a radio source. Radio astronomers found it in the 1970s. Okay? But M87 star follows the same rule. M87 is the big galaxy. I don't think I have a picture of M87, but M87 as a galaxy would probably look like this. This may be M87, I'm not 100% sure. And maybe that is the famous jet in M87. But anyway, yeah, so M87 is a so-called elliptical galaxy, which looks like that. And the black hole in the center is called M87 star. So M31 star is the name of this guy. It's not a very famous black hole. It's extremely dim. Our black hole is also extremely dim, but because it's relatively nearby, we study it easily. But this guy is much further away, and we have hardly any information on that black hole, accretion or anything. But the mass is around 10 to the 8 solar masses.
Thank you very much, sir. My question is on the observation you showed earlier where whether it is in our galaxy or the other one, there were stars kind of orbiting, we found out. But how did we even know where to point our telescopes to look at the center of the galaxy?
Yes. That is a story that's developed over decades. People have studied the dynamics of the galaxy. We know, so initially all the work was done in optical astronomy, using optical telescopes. And optical telescopes have a problem. Let's see if any of these pictures will. These are not great, but yeah, let's take any of these pictures. So let's look at this is a picture of a galaxy similar to ours. You see all these dark regions, black regions. Those are regions which absorb light, what's called dust. Galaxy is a complicated place. It's not just stars. There is gas, and there's also something called dust. And this dust absorbs light. It doesn't allow light to go through. And so in our own galaxy, if you look in different directions, you can see nearby objects, but dust stops you from looking further out. And especially for studying the very central region of our galaxy, it's very hard to do it with ordinary optical telescopes. Infrared is where you get the best information because infrared is able to penetrate through the dust. And so all the work I showed with the stars, etc., was done using infrared instruments on telescopes. But before that came along, people were already studying the dynamics of what's going on in our galaxy, and we knew things go orbiting around the center. And then with better and better instruments, people were able to go closer and closer to the center and see things are continuing to orbit around something that looks like the center. So I think people had a pretty good idea of where the center is. Not precise, to the accuracy we are talking, but rough location. Things are, and in fact, they were even going around faster and faster. So all that information was there. So they certainly knew where to point, rough direction. But they didn't know exactly which was the central point. But, you point a telescope, you get a whole area, and that's what those pictures were, those movies were. You get a picture with all these stars, and then you see that all these stars appear to be orbiting around one point. You didn't know ahead of time where that point was, but it's in that area, And now you know exactly where it is. And it turns out that that is exactly where this guy, Sagittarius A star, happens to be located. That guy's position we already knew very accurately. So I think it's kind of a long story of many different threads all coming together, which culminated finally in that particular experiment.
I know we have several more questions in the audience considering the vastness and depth of the subject, but unfortunately we must sort of wrap this up. So I'd like to thank Professor Ramesh Narayan for his time. And